Hello everyone, I am Claudiu Mihali, and in this presentation I'm going to talk about the case for adding privacy-related offloading to smart storage. Smart storage is one possible way to address the bottlenecks related to data movement in distributed systems. The idea behind it is to offload computation to storage nodes in order to take advantage of the high read and write bandwidth near the storage. This way we can minimize data movement and improve performance. Even though smart storage has been around for a long time, its mainstream adoption only began recently, when computation offload started to be available in the cloud, a notable example here being Amazon Redshift Aqua, as commodity hardware with the Samsung Smart SSDs, and as appliances like the Pliops computational storage. In the past, the focus of smart storage research has been on offloading user queries with high performance and efficiency. While this direction is important, in order to ensure that the usefulness of this offloading remains relevant going forward, we explore how to address more recent challenges in the current paradigm. Specifically, we study how to add system support for enforcing data privacy rules. This is a simplified view of a classic data processing pipeline where the data retrieval is done at the storage level and the actual query computation is done in the compute nodes. When we add smart storage, the user query computation can be partially or fully offloaded to the storage nodes. In order to integrate data protection in this system, we look at data perturbation. Data perturbation is a privacy preservation technique that alters data items or query results in order to disguise sensitive information while preserving the properties that are critical for building meaningful data analytics systems. These perturbations can take place both before and after the query-specific computation. And if they are computed at the level of the compute nodes, the user query offloading can become incompatible with the perturbations that are executed before. In this work, we address this incompatibility by studying how to offload data perturbation to smart storage and what is the cost of this operation. For the data perturbation, we chose an off-the-shelf algorithm, 3D rotation perturbation. In a nutshell, this algorithm functions as follows. First, the columns are randomly shuffled, and then data items are grouped into triplets. Then, a 3D rotation is applied to these triplets in order to generate new data points which will represent the perturbed dataset. As a motivation for choosing this specific algorithm for the data perturbation, we mentioned that there is mathematical proof that several machine learning models are invariant to rotation-based perturbations. In this simple graph, we plot the accuracy of some popular machine learning models that were trained with original and perturbed data, and as we can see, the differences are negligible. Then there is the point that this transformation is based on matrix multiplication, which can be efficiently implemented in hardware. And finally, this transformation is often used in data privacy research as a first step in other more complex privacy-preserving algorithms, making it ideal for initial exploration of implementing data privacy rules in hardware. In this work, we extend Caribou, an open-source FPGA-based network-attached smart storage solution. The main advantage of FPGA-based smart storage is that we can leverage pipelining and data-level parallelism to perform in-storage processing at line rate without reducing the read or write bandwidth. The main features of Caribou are the following. It exposes a simple key-value store interface. It has an accompanying client library that operates on Parquet files, which is a columnar file format that is widely used in distributed data processing frameworks. It supports multiple tenants per node, and it works at 10 gigabit line rate for virtually any mix of read-write operations. In this figure, you can see the block diagram of a Caribou node with the existing modules and the ones that we added in our work. First, our prototype offers a software component that pre-computes rotation matrices upon file storage and provides the right interface to clients for accessing data. The software component has been built over the existing client library, which is implemented in Go and has bindings for Python. Then we added two hardware components for data decompression and perturbation. As you can see, the read path is flexible and can either perform or not the perturbation step. So we included mechanisms that allow clients to access either raw or perturbed data, but the access control enforcement is orthogonal to our work. Since we use Parquet as the underlying data format which stores data in columns, but the perturbation works on tuples from rows, we need to provide modules to translate between columns and tuples. These modules are not Parquet specific, so they can be used with other columnar file formats, and what's even more interesting is that this design could also be run on row-oriented data with little modification and no loss in performance, thus introducing a lot of flexibility. From the perspective of a software client that wants to store some data, the workflow is as follows. First, the file is read in memory in order to compute the perturbation key. Then, the key for the rotation perturbation is computed client-side and is stored in the key value store. Finally, independent of the key computation, the Parquet file is divided into pages and stored using the same operations as in Caribou, so we do not have any additional overhead associated to storing the file or updating it over time. Now the workflow for retrieving the data. We have two primitives for data retrieval, get and getPerturbed, which are used for accessing individual pages from a stored Parquet file, either in raw or perturbed format. These primitives are composed in order to build more complex access patterns, such as getting a whole file or individual columns from a dataset, or performing perturbations selectively on specific columns that contain sensitive data. The logical steps that are done in this workflow are as follows. First, we get the perturbation metadata, which will be buffered inside the storage node to be used with the next perturbations. These mechanisms also allows us to easily and flexibly change the key to be used with a specific dataset throughout its lifecycle. Then, we get the file metadata, which contains information about how to construct the file from its pages. Then the pages are retrieved, and finally the file is constructed client-side. As we saw in the overall block diagram, the hardware implementation consists of 4 modules. First, the data coming from the storage is decompressed. Then we do the translation between the columnar format in which the data is stored and the row-based format required by the rotation perturbation. Then we do the perturbation itself. And finally, we do the reverse translation back to the columnar format. Since most distributed storage systems use compression for the efficient use of resources, we have implemented a hardware module that does snappy decompression, which is an open source algorithm commonly used with Parquet files. In this algorithm, data is encoded as either literal bytes or as references to the window of recently emitted data. The FPGA implementation consists of a state machine to control the logic and a BRAM memory window to hold the contents of the data window. Since one individual module does not function at 10 gigabits per second, we deployed multiple modules such that pages coming from the storage are decompressed in parallel. The translation between the columnar data format and the row-based format is pretty straightforward. We buffer pages into 3 FIFO memories and extract one data item from each memory to form a tuple, which will be fed to the rotation module. We perform the exact reverse when the data is exiting the rotation modules, so the whole transformation is done transparently and the Parquet file can be reconstructed. The rotation perturbation module implements the multiplication of a 3x3 matrix with a 3 vector. It works on double precision floating point data, and it was implemented using high-level synthesis from C++ code to avoid control flow complications. Again, we deployed multiple data parallel modules to achieve 10 gigabit line rate, and for the exact throughput value of one module and how we computed the necessary number of data parallel modules, I invite you to take a look at the paper. For our evaluation, we used a dual socket server to emulate the client, a Xilinx board with a Vertex UltraScale FPGA and 64 gigs of memory for the storage node, and they were connected through a switch with 10 gigabit networking. The evaluation considers the scenario of individual clients storing and retrieving data from the key value store, simulating the behavior of cloud tenants running machine learning jobs. The FPGA circuit was instrumented to benchmark the individual modules, and the main measure that we used was the throughput of the value processing pipeline. In these graphs, we plot the throughput as a function of page size. This is because the hardware module provides streaming operations with a fixed overhead per input page, so their performance is independent of the total file size and is only impacted by the page size. As we can see, both the decompression in the worst case and the privacy pipeline can sustain 10 gigabit line rate traffic, and since the modules use streaming interfaces, they can be combined with other offloading to take place on the FPGA. An important factor when designing systems with FPGAs is how many different types of processing can the FPGA platform provide. To answer this question, we need to consider the resource consumptions of our prototype. As we can see, the modules use only a fraction of the total configurable logic blocks and the signal processing units available on our Xilinx chip, while the on-chip memory usage is a little bit more accentuated, and this is because the decompression module incorporates large buffers. But overall, the prototype occupies only 1/3 of CLBs and half of VRAMs, allowing for extensions with further more complex data perturbation logic or with other types of query offloading. In summary, our contributions in this work are as follows. We highlighted the importance of including privacy-related offloading in future smart storage solutions. We presented a general pipeline structure for implementing rotation-based perturbations in FPGAs matching the 10 gigabit network rate by design. And we provided an open-source implementation that enables transparent integration with software applications written in high-level languages such as Python. Thank you for your attention. I will now take questions, and if you want to discuss further, feel free to reach out at this address.
Thank you, Claudio, for the nice presentation. So we do not have any questions from the Slack. But yeah, audience, please, feel free to ask questions. In the meanwhile, I have a small question. So your FPGA platform is currently can deliver the 10 gig, line rate. So I'm wondering if in the future we have, faster NICs with, 100 gig, 200 gig. Is your design able to, scale to that line rate?
Yes, actually, we did a little study in the end of the paper where we looked into how can our design approach these faster network rates, and we found out that the main resources of the FPGA that are consumed when developing for a faster network rate are the logic and the DSPs, and up to what we found is that up to 25-40 gigabit network speeds, the overall area of the FPGA is sufficient, but if we go further, that can be a problem. We do not really have any more space for additional processing. So in the future, probably if we have more performant FPGAs with more performant DSPs, or even with ARM cores, so that some of the processing is offloaded to those cores, it of course can be improved and scaled.
Okay, sounds good. Yeah, another question. So when we talk about, offloading application logic to smart storage, so a lot of time we need to, rely on the host IO stack, to send the data to your, FPGA or other type of computational units, right? But instead, we cannot, have the FPGA directly read the data because the data, excuse me, the data is usually managed by your upper level, file systems or, your database engines. So I'm wondering, in your case, so are you relying on, the host IO stack, to send the data to the FPGA and the FPGA can do computation? And do you see that, IO stack, during this, entire pipeline, it's causing any potential bottleneck?
So currently in our implementation, we have a client library that is specialized on Parquet files. So basically, the data is stored on the FPGA, and it is just a parquet file is decomposed such that it can be easily stored on the FPGA. So the sort of the file system is encoded inside the storage, the FPGA storage.
All right. We have another question from Flag. So yeah, go ahead, unmute yourself and ask your question.
Hi. Interesting talk. Thank you. Have you looked at dimensions of data vectors beyond 3? Previously, you mentioned what happens when we increase the line rate, what happens to the hardware resources. A separate question might be, and I wonder about it, what would it take when we increase the dimension of the data to 4, 5, 6 dimensions? You're going to need to do the matrix multiply becomes harder and more hardware resources to maintain line rate. So at what point does that become the bottleneck rather than the line rate?
Yeah, so currently the data dimension, so the number of attributes of the data can be arbitrarily high. It's just that the rotation is performed onto triplets. So this is why we have these 3 metrics. But of course, this can be easily modified to apply the rotation transformation onto a bigger dimension of data to have rotation matrices of higher dimensions. And this will only have an impact, a cost impact for the necessary buffers and for the DSP logic that performs the rotation. So yes, this will require additional FPGA resources, but it's not. It can be implemented pretty easily as long as you have the resources to do so.
Thank you.
Thank you for the questions and answers. So yeah, I think I have a last question. I'm wondering, what's the motivation behind this project in using FPGA instead of, ARM cores, as the computational power? Is it because, the tasks that you are focusing on is very, computational intensive, that cannot be really accelerated by low power ARM socks?
So basically, FPGAs are very good at parallel processing. So we can do the data processing. We can do it in pipelines in order to have a very consistent data rate. So some parts of the data processing might be suitable for ARM cores, but if you take into consideration larger processing pipelines, you can arrange them inside the FPGA such that you cannot achieve the same throughput with ARM cores. So this is why I was telling previously that if you use, there are more performant FPGA platforms coming that have embedded ARM cores. So if you use those, you can offload some part of the computational pipeline to the ARM cores so that everything becomes more efficient. But overall, you can use the FPGA to have much more consistent throughput compared with only using ARM cores.
Great. Thank you, Claudio, for demonstrating to us another interesting use case for using smart storage.